All right, so today we're on the 15th lecture. We're talking about acyl halides. And like always, we're going to start with our chart. So our chart is split into two divisions. We have our electron donors over on this side of the chart. So both nucleophiles and bases are electron donors. We have electron acceptors on this side of the chart. And these are things that pop up over and over. So we see that anything that's negatively charged tends to be a decent donor. Um, another way to show that is anything connected to a metal. So that the thing that is connected to a metal tends to take on a negative charge. Um, Alcohols, amines, double bonds. Actually, it's probably better to put amines here, seeing as they tend to be better nucleophiles than alcohols. Alcohols are less nucleophilic than amines, less basic than amines in general. Um, and then we have our non-nucleophilic bases. These are things like bulky bases like KOTBU, LDA, and another very common one is NaH. This isn't bulky, but I put it here as a non-bulky, non-nucleophilic base. It's a hydride, just like LAH is, but LAH tends to be nucleophilic, where NaH is only basic. So that is the difference between LAH and NaH. LAH will attack into a carbonyl, will attack into an electrophile, but NaH will never do this. So electrophiles, you have your carbocations, you have your things with leaving groups. So that's your halogens. Um, that's your positively charged oxygens. That's your, big bulky oxygens. And we're actually going to see the definition of a leaving group can change depending on situations. And that's kind of what we're going to go into today a little bit. Strong acids, you have HX, HCl, HI, HBr. H2SO4 is another common one. And again, a review. If you see AlX3 or FeX3, we're dealing with benzene being the nucleophile. All right. So we added something last class to the electrophilophile section, and that was an epoxide. So epoxides act just like carbonyls, but they have the extra variable of being able to add into two different carbons. So you have to decide which carbon it adds into depending on the situation. So let's do some practice problems. There's been a lot that we've covered the past few classes. We have a test next Friday. So I just kind of want to make sure that you guys are keeping up with where we're at. Um, so here's some practice problems, and we can spend a few minutes trying to go through them, seeing if you can figure out the answers to these, and we'll talk about how I would solve these if this was on a test or something. I guess since this is online, I don't necessarily have to give you guys as much time. In theory, you can pause it, but for the people that are here, take a minute and try it. It's a good opportunity to test yourself. If this was a test I gave you today, how well would you do? All right. So I'm going to start going through them. I would suggest you guys keep working. Double check your answers every once in a while to see if they match up with mine, but hopefully this is all review and this is something, all stuff you've done before. So this Grignard, this is a negatively charged, so we're basic. We're going to add into the less substituted. So this is about speed, right? This is a really unstable negative charge, so it's going to add into this carbon as opposed to this carbon. It's fast. It wants to go to the less hindered side, right? Getting in over here would be harder to do quickly. So that gets me to this point where I have this. Another common mistake people make is adding a carbon here. There's no carbon at that location. So be careful here. There's only 6 carbons in this picture, and they're all part of the benzene. So I can't add another bond out here. All right, so I go up like that. Then I'm going to protonate. And I would suggest going through this mechanism every time you see something like this, not only because it's good habits and builds good intuition, but because I think it will help you minimize mistakes on a test. So one of the most common ways people lose points is dropping a carbon, dropping an atom, moving things around that shouldn't be moved around, drawing each step out, think about each step, trying to keep track of everything, I think is a good practice. So this is one of those reactions you just have to know. This is MCPBA. Um, I'd be okay if you did ROOR, like if you knew that some sort of epoxide makes this. But I would be very familiar with this. It's going to be useful on synthesis and other kinds of things. All right. These kind of questions are asking, what am I missing? So the first way I start to approach these is I say, well, how do I balance this reaction? What is missing between this step and this step, right? So, um, my first thought is, well, there's 2 hydrogens here, and there's only one on that carbon in the starting material, right? I've somehow added, not only have I added a hydrogen, but I've added a hydrogen with 2 electrons, right? I've added a hydride. And since I've added it to a carbon, I need a nucleophilic hydride. So I need either LAH or sodium borohydride works as well here. That was the other alternative. I'm cool with both answers. I'd be able to recognize both answers. All right, these are nucleophilic hydrides. All right, this is a very similar question. What's up? I don't think was that okay. On this one, notice instead of adding another hydrogen, right, there's already one hydrogen on here. I've added a carbon. So I need some sort of negatively charged CH3 group. If I want to make a carbon negative, the most convenient way to do that would be using a Grignard. So that would be my answer, right? I need both this CH3 and the electrons that it came with, right? So that those electrons are represented by this lone pair. All right, this is the opposite. So I need to turn this alcohol into a carbonyl. I have no new carbons or anything like that. I actually lose a hydride here. So the way that I do this, and you don't need another mechanism, this is PCC or PDC. They stop at the aldehyde instead of oxidizing all the way to carboxylic acid. It's a very useful thing to know. I don't know. It's not super intuitive, but like it's weirdly easy to memorize, I think. I don't know. Um, okay.
Dr. Little,
What's up?
there was a question in the chat just to let you know.
Oh, thank you. So yeah, sorry. For both, that's a good question. So he's asking Why do you not need like a step two H2O? You do. Um, Sorry, I should be more disciplined and use it. It's implied, to be honest with you, for the most part. Like I don't think anybody's going to take points away if you forget to put two H2O. Because it's implied. If you're an organic lab, and ever run an extraction, at the end of every reaction, we tend to run an extraction which has water in it, and so we do quench with water every reaction kind of by default. I mean, technically, PCC is also quenched with water. We just don't write it because we don't write out the full mechanism. But that's a good question. Thanks for alerting me to that. All right. So this is the same question, but I get two different answers, right? So I'm starting with an epoxide, and the key thing to keep in mind with epoxides is I have two different carbons I can add into. Um, I see ethanol, and so my first thought is, where is it in the final product? So to me, that looks like the ethanol, and that looks like the ethanol. So if I think about what had to have happened, this ethanol almost, this ethanol would have had to add into this carbon here in order to get this product. That is the more substituted carbon. So I need an acid. All right, the acid helps add to the more substituted carbon. All right, acids add protons, so that's more substituted. That means that when I add to the less substituted down here, I need a base. So I would use a non-nucleophilic base. Sodium hydride, sodium terbutoxide could work as well. LDA could work. But yeah, you need basic conditions to add to the less substituted. So that's what's happening here. All right, so that's a review of kind of the last few classes. If you're able to follow that, if that all made sense to you, then I think you're headed in a good direction. If not, well, now you know what to study. So go back to the lectures either titled epoxides, oxidation reduction, Grignard, and hopefully you can catch up using that. Hopefully that was a good kind of check on where you're at in the class and kind of where you need to go from here. So this is called an acyl chloride, and it's especially electrophilic. Can someone tell me why this might be an especially electrophilic carbon?
Because it has a carbonyl and a leaving group.
It has both a carbonyl and a leaving group. It kind of is representing like all of the parts of the electrophile chart, right? Like when I look at electrophiles, like I'm seeing leaving groups and carbonyls. Like that is most of this side of the chart, right? So something that has both a leaving group and a carbonyl, I mean, this is a this is a great electrophile, right? Um, so here's the question. Do we treat it more like a carbonyl or more like something with a leaving group in the mechanism? So what I want you to do is try to take a guess at the mechanism and the product. If it's wrong, we can fix it. But give me a try. What do you think this is going to look like? What is the product going to be? So a lot of you guys' first intuition is probably, hopefully this, right? You have nucleophile, you have a clear nucleophile, you have a clear electrophile. Nucleophile attacks electrophile, and probably a good amount of you guys did something like this. This is technically incorrect. Um, but it's practically correct. And let me explain what I mean by that. So what happens actually looks like this. This was the most frustrating thing to me when I took organic chemistry. So I know it's going to be something that a lot of you guys want to do. So the reason why we draw this is because this exists. This is a known intermediate. This is an isolatable intermediate. Every time we draw a new picture on a mechanism, we're saying that that represents something that can be isolatable. It is an energy minimum. Like there is a point in time where this actually exists and is somewhat stable. This is called the tetrahedral intermediate. Okay. And what I want to do is I want you guys to get in the habit, if there's a carbonyl, we add into the carbonyl, no matter what else is attached to it. However, there's a phrase I want you guys to say in your mind. After you, it's in this bold here. After you add into a carbonyl, it wants to reform. It wants to reform. If there's a heteroatom there, if it will. If there is a heteroatom there, it will. If there is not, it will not. So, what I mean by that, I add into a carbonyl. I broke the carbonyl. Every time you break a carbonyl from now on, I want you to think, can I reform this carbonyl? Well, the initial answer is no, this carbon's got 4 bonds. But can I break a bond to make room for this carbonyl to reform? Do I have something I can kick off? Do I have a leaving group? The answer in this case is yes. I've got this chlorine I can kick off. Sorry, forgot that charge. No, what am I doing? I'm going to draw that more like the last step, even though it's less right. Okay. So every time you add into a carbonyl, you form this tetrahedral intermediate. Then I want to say, I want to reform the carbonyl. Do I have something I can kick off? In this case, I do. I have that chlorine. I get here and I deal with the charge to get this final product. How many of you guys got the final product but the wrong mechanism? I imagine that's pretty common, right? I at this point I hope that you're in the habit of replacing leaving groups. That's all we're doing here. But we're adding this kind of extra step right in the middle. That this 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 exists in real life. So we need to depict it. It's the correct thing to do. But ultimately all you're doing is replacing this leaving group with this. Your substitute is a substitution reaction. Um, so like ultimately all you're doing is taking a nucleophile, taking a carbonyl with a leaving group and replacing it, right? But there's an extra step in there that we need to account for in the mechanism. And that matters. It does matter. All right. So now I want you guys to try a couple reactions. Do the product and show me or do the mechanism, show me the product. Someone asked, do you need to like point out that this is the tetrahedral? And no, I don't. Please, please don't worry about that. I was just defining that as a term that might come up every once in a while. But yeah, I find that if you make people do stuff like that, they end up just memorizing the words and not memorizing, like not knowing the concept, right? Doesn't just writing hydride shift doesn't mean that you know what a hydride shift is. Um, so no, I don't care that you write tetrahedral, I'm an idiot. But I do care that the mechanism is correct. So I'll give you guys a couple minutes to get started on that. All right, I'm gonna start going through this again. That's just for the sake of time. I want you guys to continue working through it, and then just go back and kind of check your work along with me as I finish these problems. So I look at this. I've got a clear nucleophile. This is amine. Um, I've got a clear electrophile. So no acid or base. So step one is mute. Step two is nucleophile attack electrophile. In this case, it pushes the carbonyl up. My carbonyl broke. It wants to reform. Can it reform? Do I have something I can kick off? The answer is yes. Got this chlorine I could kick off. So I'm going to get to this. Let me redraw this more suggestively. Now I need to deal with the charges. So I'll use that chlorine to come through and take that proton. Just a substitution of that chlorine. I'll try to leave the previous example up for you. So I see a metal. The first thing I'm going to do is draw out the charges. Makes it a lot easier to see. All right. Now I see a nucleophile in this OH. I see an electrophile in this carbonyl. I'm going to go in here, kick up that carbonyl. So I broke a carbonyl. What does it want to do? Someone say it. When I break a carbonyl, what does it want to do?
Reform.
It wants to reform. Thank you. Can this reform? So technically, this, you know, isn't as good of a leaving group as a chlorine, right? This isn't traditionally thought of as a good leaving group, but in this case, this will act as a leaving group. Any heteroatom, for the most part, will act as a leaving group, and we'll talk on Monday about some of the exemptions to this. But here, You kick off that other group and you replace it. So any sort of heteroatom, any oxygen, any chlorine, any bromine, we can reform the carbonyl and kick it off. This is actually called saponification. It's how soap is made. So sodium hydroxide, the other word for this is lye. So if you've ever made soap or if you've ever watched Fight Club, they use lye to make soap. Lye is just sodium hydroxide, and this is how it works. It adds into um, some of the esters that are found in fats, and it turns them into carboxylic acids. Here's another reaction. We have a clear nucleophile. We have a clear electrophile. Nucleophile adds into electrophile, pushes up those electrons. We broke a carbonyl. It wants to reform. Is there something I can kick off? This carbon already's got 4 bonds, so I need to be able to kick something off. In this case, I do have a bromine I could kick off, and I do. Oh, I lost this. Sorry. Now I've got to deal with the charge. So I'm going to use the bromine to take the proton. So David asked, why did sodium hydroxide add into this carbonyl? Sodium hydroxide actually is not a non-nucleophilic base. Sodium hydroxide can be a nucleophile. So I don't put it in the, sorry to fly around. It's not here. Sodium hydride is, but sodium NaOH can be both. So you have to be careful with NaOH, right? NaOH on a primary leaving group will act as a nucleophile. You will do the substitution. So sodium hydroxide can add into electrophiles. All right, so this one adds just a different step, right? Notice I've got an acid. So step one is always dealing with the acids or base. So acids protonate electrophiles. So uh, so actually, well, technically it does this. Then the nucleophile adds into the electrophile. So something kind of interesting happens here. Um, so I broke a carbonyl. The next thing that happens is I want to reform that carbonyl. Um, the, the problem is that this leaving group is to kick back off. Um, to kick this back off is more favorable than to kick this back off at this point. Why? Why would this over here be a better leaving group than this? Why would I be more likely to kick off this oxygen than I would be to kick off this oxygen?
Because of the positive charge, which makes it a leaving group.
Because it's got a positive charge, right? So it certainly does happen that this gets kicked off. In fact, this reaction is entirely reversible. That can happen. But in order to kick off the other oxygen, which is our goal, right? We're trying to substitute one thing out for the other. What, how do we get a positive charge on the other oxygen?
You give it a hydrogen?
I give it a hydrogen, and I'm going to give it the hydrogen from the other oxygen. So, um, I'm going to draw it technically how, correct. So what happens is this hydrogen gets taken and then this oxygen takes it back. I don't know why I'm incarnate. So this is called a proton transfer. But why did we take the proton from this oxygen and put it onto this oxygen? It's to make that oxygen a better leaving group. We end up with this. So I know that feels like a lot. It feels like a lot of steps going on here. But if you think about why we're doing the steps, it cuts down on the memorization, right? Essentially, this is the best leaving group here.
What?
So we want to make this the better leaving group, right? We can kind of look at this and say, we're trying to substitute this ethyl O out for this methyl O. We can assume that's going to be our product. So how do we kind of get there? We we make this one the better leaving group, so that way when we reform the carbonyl, we can kick it off. What am I doing?
I'm a little confused. Could you re-explain? We don't kick off the ethyl OH we put on there.
So you do. Okay, so let me show you a different picture. First of all, this reaction is called a transesterification. Why is that? What does that mean? It means we're going from one ester to a different ester, right? We've changed esters, right? Transesterification. This is one of the few times we get to use a reaction name that actually describes what's happening. So that reaction above, if I balance it out, looks like this. If I write it out, it looks like this. This is a completely reversible reaction. Because this leaving group isn't a better leaving group than this one necessarily, these things are in equilibrium. This reaction goes back and forth, right? In a way that the other ones didn't. So if I look at this one, if I look at this, a bromine leaving group would be a lot better of a leaving group than an oxygen leaving group, right? Bromine is a better leaving group than just an oxygen. It just is. But this oxygen isn't a better leaving group than this oxygen. So you can imagine that for every time you get this, the reverse happens where you get this, right? These two things are going back and forth and back and forth. So in order to do transesterification, If I wanted product A, how could I do it? How could I favor getting product A versus product B? Anybody have any ideas?
To increase the concentration of your base or of reactant B.
So the key is if I want reactant A, if I want product A versus product B, I need a lot more ethanol added than methanol, right? So I need more of this. So most of the times more of this equals more of this. Whereas more methanol would equal more of product B, right? It's reversible, right? If I want more ethanol adduct, I add more ethanol. So a lot of these transesterification are we use ethanol as a solvent, right? We add like millions times more ethanol than the starting material, and we push the equilibrium all to one direction. Um, that's a kind of insignificant point, but it's important to think about like kind of the quality of the leaving group matters in these kind of substitution reactions. So I can get this alcohol to leave, even though it's not a great leaving group, because I can overload it with this, right? I can switch out that methanol with ethanol if I give a ton of ethanol. But this one, I can do a 1-to-1 ratio because this bromine is a better leaving group than the alcohol, the subsequent alcohol will be. All right. If we add more ethanol, we get A. Add more methanol, get B. So it's reversible. It can go back and forth in a way that the other ones can't. Okay. So that's the most complicated mechanism we're going to do today. But this is kind of foreshadowing some of the mechanisms that might be coming ahead. This idea of doing a proton transfer to make one side a better leaving group than the other side is something that we do run into. So let's go back. Let's take um a palate cleanser, eat a little cucumber. What is this product going to be? Going to go ahead and draw the charge out. Nucleophile attack electrophile. Push up into the carbonyl. So what I want to get at with this is that even in this reaction, I want you to be thinking, I broke a carbonyl. Can I reform this carbonyl? Is there anything I can kick off to make room for this carbonyl? No, I have no heteroatoms. I have no oxygens or leaving groups of any kind. Carbons are terrible leaving groups. I cannot form this carbonyl, so it gets protonated. Right, we've seen this before, but now through that same lens, there's no heteroatoms here. There's no leaving groups of any kind. Carbons are the worst leaving groups you could possibly imagine. So this cannot happen. So we just protonate and move on. We don't reform the carbonyl like we do when we have a leaving group present. Now think about this reaction. Do the mechanism. Think about it. So just like before, I'm going to put the negative charge on the carbon. Magnesium's got a positive charge. Nucleophile attack electrophile. Push up into the carbonyl. Every time I break a carbonyl, I'm looking for a reason to reform it. Do I have something I can kick off? Do I have a leaving group of any kind? Yes, I do. This chlorine. So that's what a Grignard does, right? It does the same thing, except instead of an oxygen nucleophile, it's a carbon nucleophile. But here's the problem. We still have a carbonyl sitting around. What would happen if there was another Grignard sitting around? With this same molecule. Maddie, what do you need to see? I'm sorry. All right, so if we do this reaction, adds in a second time. I just broke a carbonyl. Can it reform? Are there any leaving groups? Oh, sorry. I'm missing something. No, it can't. There are no leaving groups. So it's sitting there and it has to quench with a proton. So this all happens together. This is all one step, or this is all one reaction. Whenever you have a Grignard and a carbonyl with a leaving group, it adds in twice. A Grignard it can't help itself. It's going to just keep going. So you'll see it written like this. What is a product here? Here, let me zoom out so you guys can see. What is a mechanism? How does this happen? Why does this happen? So this 2EQ just means two equivalents. That means two versions of this. So for every one of these, there's two methyl Grignards. So I've got my nucleophile, my negatively charged methyl group. I've got an electrophile on this carbonyl. Whenever I add into a carbonyl, it goes up. This carbonyl wants to reform. Can it? Yes, because I've got a leaving group. Then now I've got my second equivalent of methyl Grignard, and it adds into this carbonyl. I've regenerated. I have another electrophile. Adds goes up. I broke a carbonyl. It wants to reform. Can it? No, there's no leaving groups. So it has to be quenched with water, and I form this. Those methyls are the same as just nothing at the end. We can see the same thing here. I mean, this is almost the same reaction, except instead of a methyl nucleophile, we have a hydride as our nucleophile. It's going to add into this carbonyl, which kicks up the carbonyl. I broke a carbonyl. It wants to reform. Can it? Yes. There's a leaving group. Now I've got this carbonyl and a hydrogen on it. I've formed an aldehyde. When the next hydride comes, I have a second equivalent hydride. It adds in. And I formed this. I broke a carbonyl. It wants to reform. Can it? No, it cannot. So it has to satisfy the negative charge by taking a proton. So notice these are the same reactions, but instead of adding two methyls, now I'm just adding two hydrogens. It's the same as doing this. This is a reaction. This is how you reduce an acyl chloride to an alcohol. It's also how you reduce carboxylic acid, but we'll talk about that tomorrow or Monday. All right. Let's try a few more. All right. In the um just for time purposes, I'm going to just go ahead and go through these. If you're following live and you want an opportunity to go through them before I talk about them, I will post this video so you can go back and kind of look through your notes. I've got a nucleophile. I've got an electrophile. Nucleophile, attack electrophile, push up carbonyl. Whenever I break a carbonyl, It wants to reform. Is there a good leaving group to kick off? Yes, this chlorine. So I form this. Now I've got to deal with the charge. I do want to point something out here, a difference between, say, this LAH mechanism and this amine mechanism. This is also an electrophile, and I could, in theory, have more amine sitting around. But if amine were to attack, if the amine was to attack and we were going to do this process again, I would end up just kicking back off this amine and doing another, just substituting it with itself. So it's not productive to keep doing that. Whereas when the hydrogen adds into here, that's not a good enough leaving group. So it's going to stay around. So the methyl nucleophile, or sorry, the Grignard and the LAH are different because this product you make after the first addition, after the first substitution, doesn't have a leaving group on it. Doesn't have a heteroatom on it. There's nothing I can kick off. So the next step is productive. Where if I were to add this in, essentially kicking this off after a few steps, I would get this again. So it's just not worth doing. But the LAH and the Grignards are. But I think if you just walk through the steps, it's pretty intuitive. Well, maybe not intuitive, but there's a pattern. And it'll help out to see this pattern over time. So this is H minus. It's going to add into this electrophile, kick up the carbonyl. I want to reform the carbonyl. Can I? Yes, there's a decent enough leaving group. It just has to be a heteroatom. Now I've got another electrophile. And when I add in, when I do this, I want to reform this carbonyl, but now I don't have any heteroatoms to kick off. So I'm going to take a hydrogen instead. Right, I've essentially reduced this all the way down to this. This is my nucleophile. That's my electrophile. I'm going to kick up. I broke a carbonyl. It wants to reform. Can it? Yes, it actually can. This is a reversible reaction. We can kick this off. But that's not really productive. That just gets us back to our starting material. So this one is one that we're going to continue talking about later. So I'm happy if you get to this point and you say, well, we're going to be here, going to just deprotonate and reprotonate. To get to this product. But this is something that we're going to talk about in the future. we're not done here. So I wouldn't, I mean, these steps are still steps I think you should be able to walk through. All right, what the heck is this? What is this voodoo? What does IPR stand for? IPR is isopropyl. So isopropyl looks like this. And then MgI. Well, I just acts just like BR. So this is just a Grignard. So I'm going to treat it kind of like this. I and BR are, we can substitute one for the other without having much problems. It's pretty common to do it. We get this. I broke a carbonyl. Can it reform? In this case, it can't. There's no leaving group. And so it satisfies the negative charge by taking a proton. We're here. I've got the nucleophile. I've got an electrophile. Nucleophile adds into electrophile. Kick up the carbonyl. Oh, sorry. I broke a carbonyl. It wants to reform. It can in this case because I've got a leaving group. So I'm going to go here. My hand's cramping. It's got a positive charge here. I'm going to use that chlorine to deprotonate it. And I end up with this product. I'm going to tell you this now. I want you to draw these mechanisms. There's going to be a part of the test that's worth a significant amount of points. That is you drawing the mechanisms. I care more about the mechanisms than I care about the products. So yes, it's useful to think, oh, this oxygen is just going to substitute out this chlorine, but I want to see that you guys can reason through the chemistry of why that happens. So that's going to be expected of you. To be able to answer like this. Like a portion of the test will probably look something like this, where I give you different kinds of carbonyls, different kinds of nucleophiles, and I just let you push the arrows and tell me what the product's going to be based off of that. Where this product is going to be worth as many points as this product. All right, so how do we form these? It's some SOCl2 will form it. If you guys want. This is a good exercise. You can see how this mechanism works. I wouldn't necessarily ask you for this mechanism, but you guys can kind of figure it out from that point. But what I care about is that you know that SOCl2 will substitute out an OH for a Cl. And I do hope you can do the mechanism. It's very similar to what we've been doing. All right. So now that you know all this, now that you guys are experts in these acyl chloride, acyl halide reactions, we can use them in a synthesis. So if you see some sort of ester, right? This is why I care that you guys know functional groups. If you see an ester in your final product, it was probably formed by a reaction with these two things. That's a safe bet. So let me do this first reaction for you, and then we'll call it a day. So I see an ester here. So I'm going to make this disconnect. I'm going to say that's the major bond I need to form, right? Just like things we've done before, I know on one side of my bond, I need that leaving group. And on the other side of the bond, I need that alcohol. And that will get us this product. So the question is, how do I make 1 and 2? Well, 1 has to come from this because it's got the phenyl, the benzene ring. 2's got to come from this. So I'm going to start with 1. In order to turn this into 1, I have to first get an alcohol here. This is the anti-Markovnikov. OH addition, that gets you there. Again, this is less important than knowing where you have to get to. Like, being able to plan this out is more important. In real life, you can always just type in anti-Markovnikov OH addition. But like, if you don't know that's what you need to do, that's what's important to me. Do you know where you need to go? Can you plan this out? Then I can get this to a carboxylic acid using KMNO4. To oxidize it to a carboxylic acid, and then to finish it out to get to 1 SOCl2. So that's how I'd use this in a synthesis. Again, 2 is very similar to 1. I've got this double bond. I need to add an OH at the end. That's going to be an anti-Markovnikov addition. That's the pH3, H2O2, NaOH. That gets me to 2. If I add 1 plus 2, that should get me to this product. That's how I do that synthesis. The rest of there's a couple more synthesis practice. You can never do too much because I think it's a good way to kind of approach the same, right? A synthesis is no new information necessarily. It's just a different way to approach the same material. It's a good way to practice the reactions, right? It's a good way to test your fluency. Is this something I can start after I've done enough arrow pushing, after I've done enough reactions? Are these things I can start kind of bridging the gap, putting together, putting consecutively? I think that it's a process where doing both sides, doing the mechanism and the synthesis, strengthen each other. Do you guys have any questions about today's class? Are there any things I could answer? No? So someone asked why I use KMNO4 instead of PCC, because PCC, I'm going to do it in Garnet. PCC gets me here, and I can't turn, there's nothing I can do to turn that into what I want. PCC stops at the aldehyde. I will be having office hours on Monday from 1:30 to 2:30, and I probably will also be having office hours on Tuesday as well. You can use Na2Cr2O7, sodium dichromate. Yeah, so you need a carboxylic acid plus SOCl2 to get to this. To be honest, you could also do this. That would also work. It's just riskier because of what we talked about earlier. You'd need a lot more of two to do it. So this would be the better reaction. So let's just go ahead and shoot for the better reaction. But yes, you need the carboxylic acid. So calling it just an OH on the end is incomplete. That is the functional group of a carboxylic acid, and aldehyde will not do that. I will try to post this as soon as I can after class. Yeah, I'm okay with you if you wanted to use PBr3 to put a bromine on, yeah, I'm okay with that. It's a little bit less like traditional, but yeah, I'm cool with it. It should work. Yes. So if instead of SOCl2 you wanted to keep things consistent, and do that. Yeah, I mean that works. To be honest, I can't make an argument. You just see acyl chlorides a lot more than you see acyl bromides in literature and stuff, and I don't really know why, so I'm cool with both. So if you wanted one to be a bromide, it would lessen the amount of things you have to memorize. But yeah, SOCl2 or PBr3 are both kind of equivalents. They do very similar things and get you to halogens, which are broadly interchangeable. Good question. Yeah. Cool. Well, I think that's it. And I hope you guys have a great weekend. I will see you on Monday, and I'll try to post this as soon as I can. All right. See you guys.
Thank you.